Hello everyone and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't be hesitate and welcome. If you have any questions, you can post them on the Handmade Network thread, forums, or on YouTube, or on Twitter, and I'll be there to answer. With that said, let's start by opening the project. And I want to go straight on to compile this and see where we left off. If you remember on the last stream, we were like discussing this. I can even open it. I don't know if it's here. We got this x86 64 spec, which was like our starter point to think about, to think a little bit more of how do we want to specify the opcode specification for the x86 and 64 Intel architectures. And we started by doing the stupidest thing possible by saying, okay, what if have one encoding, we have everything that the disassembler could in any moment need to get the data information, and just write, like, it can be a text file, this is a plain text file. I don't know, we can probably have this kind of idea. I mean, we just be repeating this stuff and etc. And later on, while we were like kind of working with that and saying like, well, what was the main purpose? And the reason that we were like thinking, well, probably it's not necessary, is because we already have this definition for what is it on the tables. We have this definition that's called EagleFly mnemonic entry, which pretty much serves the purpose of this specification. But here's the interesting part, and this is the thing that I thought that it was important to mention, and the reason that I step back and take this into account again, so we can like reconsider. And this is the reason why. There's an important thing on the architecture of this system. The EagleFly disassembler. I can even write it on Milton, so it can be explicitly. I can write it and draw it explicitly. So let me open Milton. I don't know where Milton is. Where is it? 636 Milton. It's not here. 64 Milton. There we go. So let's see. Oh, there you go. Okay, so I can just say here that I have I don't know what day state I'm gonna put a day, I guess, but I'm gonna call it here EagleFly just this is terrible. Architecture. uh, so this is the architecture that we are like um, thinking on. Right now we have something like this. Um, I'm gonna call here, I don't know, the December. Straightforward. And we got, I don't know, I'm just gonna circle it. Oh, Jesus Christ. Well, forget about circles. We're just gonna do it like that. But I can try. There you go. We have this assembler. We have as input our we can call it our text file, a text section, or even just the P file. We call it. We have a P file with all the opcodes as machine code, and we can get here an ASM file or another a higher level representation of the data information that of the instructions that the P file has encoded into it. So this is the pretty much straightforward thing that that somebody can think about and say like, oh, what does a disassembler do? Well, it is this, like a global context of what's happening inside the process, But we have if you want to expand this idea, this is pretty straightforward. There's just one line going on there, so there's not a lot of thing happening there, or at least we cannot see it at first glance. What's happening inside the disassembler. So we can have an explosion here. We can, as they call it, with this model parlance, as they call it. But if we continue with this kind of showing this off, the disassembler has this kind of callbacks, which in this case, let's not call it callbacks. This request to the tables. I'm gonna call it here the tables. Go. I want this here. So I'm gonna call it here the opcode tables. Opcode tables. Which is right now all the thing that happens in that initialization process. So right now we don't have any kind of definition of this. We have definition of, we can call it we have the basis of it, we can say, the basis of what we need, or what we need from the opcode tables. We have it, that's important. But and we can call it, this is this can be go like this, big direction. We request something, and the opcode tables returns we can call it the mnemonic entry. That's the thing that he needs. So we have our mnemonic entry as the thing that the opcode tables return, and here we can call the ID, or the instruction ID, whatever the thing identifies the thing. And we pretty much define this API. That's something that we already have, and that's good. This is like the thing we already define in the system. But here's the interesting thing. We found, since we have here like a kind of retribution thing where it's almost like these opcode tables are isolated and can work as a module, So the opcode tables can pretty much are here just to service the disassembler, and that's it, you know. So they don't have anything to do. They don't need pretty much anything but to think about. I mean, they are. We can think of them as totally independently, you know. So that's the point of what I want to mention here, and it's like there's since it's a module and it has like these two movements. One thing that we as developers or whatever, whoever who wants to use this disassembler is going to need to, let's say in the future, imagine this is like this is a thing I was thinking about yesterday, like, you know, I mean, this assembler, well, right now works pretty straightforward. You know, we can just add all the mnemonic entries in a table or something, I don't know, in a file, just load it up and try to find it out somehow, you know. That can be, you know, I mean, that's not uh, that's the first thing that comes to mind when you see this. But what happens if a user, you know, someone that's it's totally uh, uh, foreign, or it's totally he doesn't know anything about the well, the internals of the disassembler itself, and you know, he doesn't probably care about how that mnemonic entry is in there, or why does the disassembler use the mnemonic entry or whatever, you know. The mnemonic entry is something that its only purpose is to serve the disassembler, and that's it. But we have to have a representation that serves the user that's working with the opcode tables, you know. And you know, that's the important part of thinking about how we want to represent the opcode tables, because right now we have this mnemonic entry, and these mnemonic entries, even though they are pretty explicit in the sense that, well, they are little right now, probably in the future is going to have more, but it's not the user API for the opcode tables, you know. Is like you know, the mnemonic entry works here, it serves this part of the purpose, but we need another API, you know. So we have two APIs. One is the disassembler API that the user can use and model to, I don't know, we can say to model to extract some, we can kill to get only the part of the disassembler, you know, disassemble this, you know. And the opcode table API is the one that serves the user to add new instructions as they come, or to retire them, if any, you know. So, you know, the ISA is something that it's fluid, you know, it's always changing. Every year they change the mnemonics, every year they change all this stuff, every year the opcodes change, and we want to have that kind of solution to that problem, where even for us, you know, which is, I mean, it's even simpler to say, well, I just want to pass. I mean, this is something that the ISA, even though it's not executable as in the ARM processor does, it's something that you can just copy and paste, you know. It's pretty straightforward. You don't have to know a lot about the syntax. Probably, I mean, we can clean up the syntax a little bit, but the things that you need, you can find it on the ISA and you can paste it. That's it. You don't have to think about internal representations of how the mnemonic entry, oh, it has a mother RAM present, or it's a recti mother RAM, or you know, this kind of crazy stuff happening, like, oh, okay, where do I find that thing? Or I mean, imagine the person that they don't even understand opcode tables, which it can be the case, you know. So we want to have the simplest and most let's say we want to have a language to express the spec, you know. It's a language to express the opcode tables that the user can see, that the user can modify, the user can erase if they want, and everything will be fine, you know. So what this means to the system is another API which serves only the opcode tables, so that every time we want to just change something, add something, we just go here, add the encoding, we add the assembly syntax, and we add whatever it means to it to convert it, you know. We just say how do I get it, you know, how do I translate this EV to something meaningful in this case, you know. So we just need something like that represents something that that we can just go and fetch, and the assembly is just gonna make the total work to solve that thing. And yeah, you know, That's the pretty straightforward thing. So yeah, I mean the important thing here is that we have another API design here, another API design problem that we have to solve it from the opcode table user side. Like, hey, we want to have the possibility. Users have read this language, the specification, whatever, and stuff. So this is okay. This is gonna be our internal structure that's gonna work as the intermediate, say we can say. So this is gonna be served as the translator. We're gonna pass from this to this, so that the disassembler can work with this, because this is what he understands. So that's what we have to do now. So yeah. So I hope that makes sense. So yeah, let me drink some water. So the thing that we were trying yesterday, it was correct. It's just that we didn't got to the point where we understood why we didn't, why it was so important to the to the problem itself. Because we have this other entry point for the user. So that's the important thing to know now. So if we want to have that entry point, and something to bear in mind here is, like, it was good, and thanks God that we found this at early stages, like right now, that we can just, like, we can try. I mean, the simplest, stupidest, and the stupidest thing possible, where we have, I don't know, the instruction string right now is super slow, super little. We can start by doing each one of these, as I explained yesterday, I guess, and we can say, where is it? Win32. We have this string here. This is we can go one by one and just add it, and probably that's the way it's gonna work. And that thing is gonna um um well, I was like thinking, like, well, I don't know if he's gonna, like, fasten up the thing and make it more faster for us to work, but I don't know. But at least the specification can work starting from this, the thing that we already have. So so let's go and do just that. Let's start doing that. So let me go to the other file where we were doing that, and I believe it's the test something, where we I copy basically everything, isn't it? And on the build of that, I have this. So one thing to think about here is, like, the tables. This is important. Even though the disassembler is a utility that is not a loop, it's not like a game where you can you have a real-time system simulation of things. Like, that's not the thing here. It's simpler than that. It's just a line. You have an input, you process, and you got an output. It's just like that. So normally, and this is important, the tables, I mean, we can let's just think for a moment, like, how does the users would use the ISA, how would they use the specification, write the usage code first. So if they have to write this stuff, they have to write this stuff and have to add those stuff if they want to. We want to have some kind of system that understands it, of course, like um, and right now we just have like groupings here. I don't know if we want to have something like a tree or something. Normally in these kind of systems they use trees, hierarchical trees, where they go from the let's say the most hierarchical thing, and go each leaf trying to find each branch, trying to find out the real opcode that this specification is meaning. Like trying to match the opcode against the specification. So yeah. And probably, I mean, it can be like a meta programming thing where you can just parse this stuff and get the tables as an output, and then we just load the tables inside as we might want. So it would be something like this. So we have and I think I need a better name for this thing. This is gonna be I'm gonna call it test. No, it's not test. This is EagleFly opcode tables. EagleFly opcode tables. EagleFly EagleFly opcode tables.cpp. I don't know if I already have that. No, we have tables.h. So up tables generator probably. Parser. I think I have a lot of parser here things that like putting another parser, it's a little bit weird, but it's this can be like this, and then we can just do that. Let me add this. Put the charger. Alright, so now we can say, well, I'm gonna call EagleFly opcode tables generator, and it's gonna be, I'm gonna kill, we have a bunch of garbage here, we can just erase everything, but we need the disassemble. Test disassemble, and I'm gonna call it, I don't know if it's renamed, I don't know the syntax, but doesn't matter. I'm gonna do it like this. Rename. I'm gonna go to the B file. I'm gonna call code, and I have test disassemble. So EagleFly opcode generator opcode tables generator and that's it. So we will have something like that. And I have to 664 spec. I don't know how they put it, like a pipeline or something, but I don't know, code tables. And this is gonna be called EagleFly. You know, this is what we want to do. And then, well, if we compile, it's just gonna be what we don't have build it bad. And yeah, I don't know if this is the way to do it, but we will find out, you know. So the first thing is like, well, if we go to the opcode table generator and open it on the code, of course, yeah, I mean this is wrong because it's not in the right path. But let me go and open the opcode table generator, and I'm gonna keep basically I don't know if we need this. Probably we need this. Define. I don't know. I mean, we don't need all of this. We just need certain stuff. So we probably want to pass that as well to another file or something, to the header file probably. So what I want to say is here, like, yeah, I'm gonna use Windows. We can choose not to use the allocation memory, but in this case we are gonna need it anyway, because we wanna polish this stuff really good, because this is gonna be something that the user is gonna use, or we are expecting that the user uses. So it has to be fast, and it has to be yeah, I mean we want to use something like that. Probably, I mean, right now this is all good, but later we want to have a better interpretation of it. So first of all, yeah, let me just clean that first, because it would be just a mess not to have this. So let me clean all this stuff. I'm gonna keep this right now here. I'm gonna say that we don't need this. We're gonna need anything about this or expression. I mean, probably some of these are good, but that's what we're gonna clean up later. Well, that's what we're gonna do right now. So I'm gonna just say that we don't have it, and I'm gonna say this is just the same, doesn't matter. I want to, I don't need this, we don't need anything of this, and we can just go straight on to there. And I'm gonna just first not do that because there you go, and there you go. So we have our EagleFly code table generator, and we have our Win32 EagleFly disassembler. Everything works fine. So now what I want to have, I'm gonna keep it this right now like this, because first I wanna do the thing that we haven't done yet, but we have to if we wanna start to clean this up a little bit more. I just feel like it's the moment to have it. So on the Win32 EagleFly CPP, we do have all these codes and information, and I mean, that's okay, but we want to have a platform layer. The standard platform layer of Win32, where all the systems that the things in this case need, even though they are two processes and they are run externally one after the other. We want them like two processes external of each other. Because probably you don't want to, and this is also about API decisions, like you want to, I mean, if we divide it, we will leave this freely to be compiled every time, so we will be generating the asset file system all the times, and that's what we want, because we want an asset, and our asset is the opcode tables. So it's like a file generator. That's all we want from this file. This is the file generator, and this file generator, of course, has to work really good, but it's independent of the disassembler itself. So this has to work by itself. Now, how do we solve? We don't want to have two platform layers, if that's possible. That's the main question here. Like, we want to have a platform layer for this, and want to have a platform layer for this. If we can avoid it, So what happens if we have one platform layer for both, and that the platform layer system so yeah, so we want to have a shared library or something like that. I mean, or we can just define, we can have just one platform layer, and define the calls as externs, of the things that we want to get call, you know. So we have the function definitions or the function prototypes for each of the callbacks that we want to get, all the functions that we're going to call from that executable, if that makes sense. And that's it, then the process returns back. We can do that. I don't know if it's too janky. Yeah, I mean, it's like thinking, we have a function call that we want to run. In this case, we want to have we could have the same one and be run. It's an interesting question. I mean, it's not truly important right now, but it's just like, well, it's something that we have to start thinking about, like, how do we want to order this stuff. We don't want to have two platform layers because there's no need to that. Of course, the basic stuff that we want probably is different for each one, since we haven't done a lot of the work for that to define, like, hey, what's gonna be the size of this, or what's gonna be the thing. We can just stay with a module. So so I think it's better if we just run it independently. I mean, forget about platform layers and just see what the API decision decides, because we don't know. Probably, we will be guessing in this case, and we don't want that. So the best thing to do is just do the usage code here first, and that's the teller, So yeah, we're gonna keep it like that. I was just gonna do something, so I'm gonna just hold on that because we don't know exactly what we want from the platform layer. I mean, we know. Yeah, we don't know exactly. So I'm just gonna keep it like that, and I'm gonna say that I'm gonna have the what's this, table loader CPP. Do we have a table loader CPP? Oh yeah, we have a table loader. What do we have on table loader? Table loader. Oh, we have this. Okay. Well, it seems like we don't need this here anymore. We can have it here. So I'm just keep it like that. Doesn't matter. And I'm gonna start here with the stupidest thing possible. We wanna create the entry, so I wanna grab. I'm gonna take all this. Forget about it. And well, I'm gonna erase it. Well, I'm gonna erase it right now because it's not, I'm gonna forget it. cd no cd EagleFly code there. I'm gonna let EagleFly. We have a lot of files here that I don't know if we use them or not, but delete. Where is the loader? EagleFly table loader. There we go. We have another, print 6 sesame. I think that's good. So I just put that on the table generator. If I compile, I don't need that. I'm gonna use standard IO. Yeah. Well, hmm. No, we don't want to use standard IO here. We want the platform probably, and this is some, yeah. Probably we want tables. And for being like reasonable, I don't know why did we. I mean, we have the disassembler, which serves the disassembler alone, and the system and the disassembler. So we probably just want the disassembler tables. That makes sense. Where is it? Tables. Here we go. Which is like the raw data, we can call it. This is the raw data. This is how the specs define, and that's it. We have so all the raw data is gonna have that here, and the intermediate representation is gonna go in the SASM alone, in the AH file. Okay, I like that. So yeah, I mean, this is good. We have the SASM tables, and we have the platform if we need to, and that's it. And here is, what's the problem? Can open EagleFly, winter 2, EagleFly says and tell us the traffic. Okay, how's it called? Oh, EagleFly. Oh, like that, okay. Load tables, EagleFly, this has some state. And I don't know why we were doing this stuff, but whatever. Well, we don't care about that. We can start again. We have a printf. We don't need a printf anymore. And that's it. So the first thing, I don't know, I'll put debug string just for being sure that we are doing this correctly. I don't know. Hello, this is EagleFly. EagleFly code tables generator. There you go. And do we need have windows? I don't even remember which was the name of this output debug string. We need Windows.h and kernel 32. So are we using the kernel? So a typo there. Okay, so if we run this, and I know we have a solution for that. Well, I'm just gonna delete everything. Clean build. Boom. So there you go, alcohol generator, and there you go. So the solutions are gone. That's okay, doesn't matter. So I can just open the debugger and start with this. So EagleFly alcohol generator.exe. And we're gonna call it like that. And we don't care about that. We can just say it's something like that. No, what did I do? No. No. Jesus Christ. No, I don't want to do that. Okay. Okay, everything seems fine. No. Open. File. Please open a file. Still Windows. And I want to have EagleFly custom debug cpp EagleFly and we have just basic here. So if we run this, we're gonna have the stupidest thing here, and we have the massage. Where is the massage? Oh my god, again. Well, I'm gonna step into it because, and it's like, oh, you don't have the okay, there you go. A code table generator, and everything is working as expected. So that's okay. That's what we want. We just want a program that does this kind of stuff. And the first thing, of course, we want to do here, for simplicity, is just like I want to open the file, So I don't know how we call it, but it was like Win32 open file. I don't know. And it was like, how does it call? Win32 allocate memory, allocate debug Win32 read entire file. Okay, I'm gonna call that, and that is on the platform. We just pass a file name, and we got debug file content, the file name, if content, we start doing whatever we want, and we can try to open it. We can try to load a debug info, we can try to load a debug info stuff. Where is the yeah, the content? And we can compile that. Course file name has to be something. In this case, it's gonna be called the x86 64 spec. And this is pretty simple. I don't know if it would be better if we, I mean, even though we define it here as our first usage case, we need more to represent more. I mean, we can just try to do all of them at once, and then we start making the parser, which could make sense since this is the API, you know. This is the API, so this is the thing we know how we want it. So let's go back. I'm gonna leave it like that, and I'm gonna go here. And well, we can even just debug that in fact we're getting the data information, you know. I'm gonna say just bum, 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 bum. I don't know if we have a close file. I don't know. We'll have a close file, isn't it? We just copy on the memory and then we close the handle. Okay. So yeah, we just that we don't need to. Okay, good. So that's it. We got the memory for the count, and I can just say F32 memory index data size equal to content data content size, and something like that. So if we step onto here as well, we see the contents, and the content is telling me that yeah, we have a content that it has has a size of 162 bytes, and that makes sense, you know. It's not a huge file, you know. And if we see the content, I'm gonna copy this onto memory. We should see the ASCII representation. There we go. We have a group 1 byte, 0 byte, blah blah blah, mod x rec x, blah blah blah. So yeah, we have our file here, which is nice. And we want to have this all across the thing, so that's good. So we have blah blah blah, there's size, and we just close it. Perfect. So now that we know that we can open it, we can just play around with it. So this is the first add. I want to go one by one again and just add them all together so I can see more about the usage cases, you know, so I can see more of this. So I want to go to the system SPP, and right here I'm gonna go here are the entries, and here I need a string back. So we got the 0305. We know that this is the encoding, and I want to have a way, I don't know, we can have something like this, like its own language. And then I can say this, and then I can I can use a lot like C syntax. I don't know. And this doesn't need this, but yeah. So let me see if something's missing here. Um, mm, okay, so this is, oh, where I am. This is not like this, is the other way around. Yeah. Yeah. I can collide this, I guess, so that we can have that. So we can just define it as string expressions, and these are the grammars that we have to resolve. And the order is already specified, so that's okay. And the yeah, because we have another one on the by here. For example, we can have, oh my god, we have here the same thing, but this on the direction will mean something different, and that's fine, you know. On the, I mean, it doesn't matter how big it is. In this case, we just want to have a compressed form my way past to the data structure that we are looking at. So I mean, this is gonna be like this. Mm. So I mean, we can, since we have where is it, a byte 01, uh, EV, GV, GV, EV, you know, they are only swap, you know. The only difference is that we have a bit, the direction bit is set, you know, 1 3 or 02. So in encoding, that's what we have. You know, have the O1. We don't see it here, but we can say it will be a little more complex because in this case we have memory to register, register to memory. This is like that. So this is the register to memory, and this has to be like this. But yeah, that's okay. Probably, yeah. So I don't know, I'm gonna happen to add other styles. Let's see. I can just try the shift left. This is not a 1 byte, this is a 2 byte. So let's go here. And the first thing here, I was like So we have 1, 2, 3, 4, 5, 6 and here we have, because they count for the same one, because this is 1 or 0. But my question is, okay, right now the one we're looking at is the memory to register, let's say, which is the case, yeah, which is this kind of thing, and we just put encoding, and we have the math and the regular RAM. So well, I don't know, I don't care, but I was just thinking like, what? Um, well, let's do this shift. Why not? It has an immediate and is something like OFA405. And we don't, I mean, for this spec, mm, I mean the assembler could know by itself that the meanings of this, and I say they could because they could, but I want to have well, yeah, so probably we don't even need that, we just need the encodings, you know, that's it. And I want to have something similar here. And to find this one, there you go. We're shifting by in media count, yeah, and we are shifting OF, and this is A4, and this is using the rec, and then the mediate, and then the mod and the rec and the RM, and then the and do we have, it's an O5, that means that is mod, it's a memory, so we're looking at this one, memory by media count, so this is the one we want. Well, we don't need this. I was just like, well, thinking about commenting. Okay. What else? What else? What else? Yeah, I mean, all this is the byte OF, blah blah blah, and the interesting thing here is like how to. We have this that this represents the width of it, you know. The width of instruction. We haven't taken into account that. This doesn't have a width or anything. It has a sign. This is a sign bit. And if we go, let me see if I have extra information in the I want to go to the instruction summary. Here you go. I want to find so we have OFA4 RBIB. This is saying the information, and well, the encodability probably is a nice thing also to have. Yeah. This is something that we already have. This as well, this as well, this as well. The only thing it's missing would be the 64-bit mode or compatibility, which we also want to have that as well. Shift left double, and probably want the context. Well, we don't want that. Yeah. What I want to have here, if this is balanced 64-bit mode and 32-bit mode, so I want to have a flag system. So flags, you are 64 E and no, I mean important, this is only for X-series. Mode 6432. And this as well. Now for the add, I want to make sure that that's also the thing. Uh, uh, and the one we have right now is an O3. We have an O5. That means we're disassembling this one. So these are valid on both cases, with the 1 and with the 2. So yeah, that's okay. Good. And I want to have a check mark. Like this is the one we were breaking or something. And the best thing possible to do is just go straight. I mean, once we play around with this ISO, this specification, and we just like, hey, we are ready to start doing the whole thing. We just are gonna copy paste the whole stuff and and start doing it that way. What we already have it here, see? Valid 6432. Okay, we have the information here. Nice. Pure line R, XM0, XMM white. Oh. So we already have the mode here. So I want to find this one. This 3-byte opcode, so it has to be 66 OF 38 OF. And this is the other one, but we don't care about that because that's vectorized. So we see P, it's a pointer. Oh no, my bad. I was reading wrong. Where is it? Is this P? Yeah, the rect field is inside the P, so it's there. And we're looking to MMX. And we have a Q, so that means a quart, pack what word. Now P uses MMX even though we are spitting out xmm1, unless they are stored on xmm1, because where is it? Here it says xmm1 with a 66. But this is not vectorized, it's p-linear. And this is MP, meaning not possible, not so yeah, the 66 makes a difference, which is a mandatory prefix. So how do we see it on the encoding? We have VX, so let me find encoding here. There you go. So they have 66 OF, 66 OF. A OF C108. So this is the one we are looking at. And now here it says that it's an XML rec. XML rec. So I'm gonna say just like that's it. And I would like to say that uh, and I just want to find out the mode its value on both, and we have a CPU ID there. Which I don't know if we want to have it. We want to have probably a family of it, you know, like to which family we're looking at. You know, these are like GPR, no, this is not GPR, it's oh no, yeah, this is GPR, and this is this. It's more like extension. Can be something like that. Just if you want to know more about the instruction. And yeah, that's it. That's all she said. So if we compile this, since that we do, we unfortunately we run out of time, but we will continue with this on the next stream. And you know, I mean trying to find out all the stuff, you know, it was like, well, since we are like the first time, probably that's the reason why it took so long to do that kind of stuff. But this is just testing and see how easy it is to do that kind of stuff, you know. So yeah, so please, if you have any questions, post them on Twitter or YouTube and I'll be there to answer. Yeah, if or on the Help Me networks as well, on the EagleFly thread, you can post your questions and I'll be there to answer. Post them related to the thing we did today, and there you go, I will answer them. So yeah, I think that's good for today, and I will see you all on the next stream. Take care and God bless you.